I hope you had a nice weekend, and today we are going to start covalent bonding. Now, as the name suggests, covalent is about two things. There is the co part, which is basically sharing, and there's the valent part, which means that it's being shared in the last shell. Now, of course, this is going to happen in non-metals. Part of the reason is that if you look in the periodic table and let's suppose we were to look at the number of electrons that they need depending on the uh, shell that they're on. So for example, if you look at group 1, then it needs to lose that one electron, right? So it doesn't really need to share anything. It just loses that one and it's good to go. And similarly, group 2 would like to lose 2. So this is basically a table of how we need them to share electrons. So if you notice, group 1 needs to share 0, group 2 needs to share 0, group 3 needs to share 0. Why? Because remember I told you that they prefer either 0 or 8. That's what they want. Now 1, 2 and 3, all of these three groups can simply lose an electron and get to 0. But if you look at the other ones, now here's an interesting thing. Group 4 shares 4, group 5 shares 3, group 6 shares 2, group 7 shares 1, and group 0, which we also call group 8 sometimes, that shares 0 electrons again. Yeah, so basically what's happening here is that you have these groups and they're sharing these electrons. But here's the interesting part. If I add the numbers together, for example, when 4 is added to 4 for group 4, that gives me 8 in total. 5 with 3, 8 in total. 6 with 2, 8 in total. And 7 with 1, you guessed it, 8 in total. So that is the preferred number that they have. And that's no coincidence. The reason that happens is that because the last shell that they're in, it wants to get 2 more electrons and it's good to go. It is stable and it's able to share that and form a substance, a structure in which it doesn't need to take any more reaction and all that. So that is why they do the sharing part. Now, why doesn't 0 do this? So that is because these are called noble gases. They have complete shell automatically, naturally. They don't need to share anymore. These are unreactive. We use another word for it. We say that they're inert and they do not usually form covalent bonds. Sure, there are a few compounds of these things that were found in the 1960s, but that is way beyond O levels or IGCSE syllabus. That why exactly do they do that? Metals do not form covalent bond. There is one case in our syllabus, which is aluminium trichloride, in which metals do form. Aluminium does form a covalent bond. But again, why does it form that is beyond our syllabus. We just need to know that if a question like this comes, we should know that aluminium trichloride, and part of the hint is that it's trichloride, not aluminium chloride, that it is covalent substance. Now there's two cases of covalent substance. They can either exist as molecules or they can exist as structures that are giant structures that have lattice in them. So, all right, so what have we done so far? Covalent bonding takes place between a nonmetal and another nonmetal. So, for example, you have hydrogen atoms, they bond with another hydrogen atom and they form covalent molecule. Chlorine atom bonds with another chlorine atom, makes chlorine molecule. Oxygen does the same to make oxygen molecule, nitrogen does the same to make nitrogen molecules. But carbon doesn't do that. Carbon actually does share, but carbon can either form a molecule, which we call fullerenes, which we'll talk about, or carbon can form giant lattices. Those giant lattices are also pretty interesting and pretty important to study, and that is why carbon offers this versatility, and that comes from the reason that carbon has 4 and it needs to share 4. All right, so let's focus on these three for now, the ones that are able to form molecules. Now, there are a few molecules that are required for our syllabus that we really need to know how to draw. So let's quickly go over it. Like, we know that non-metals, they want to gain electrons, they share electrons, and in the molecule there are different atoms that are sharing different number of electrons, sometimes same number of electrons. But what you have to remember is that they want to get 8 overall. It doesn't matter which one shares less, which one shares more. As long as they're getting 8 for each other, that's perfectly fine. All right, so let's start with a very simple one. And let's see how we can make that molecule. Okay, so let's start with hydrogen. Hydrogen is basically hydrogen atom that is simply one electron in the structure. So what it does is that one hydrogen atom shares electrons with the other hydrogen atom. So these are two hydrogen atoms. Now each of them has one electron in this last shell, so that's how they are. And in fact, they just have one electron, so that is technically the last shell. So what happens? They will combine together. Each hydrogen needs one more. So what they're going to do is that they're going to share one electron with each other, and they're going to form what we call a hydrogen molecule. Now this thing is not H, this is H2. This 2 basically tells me that there's two atoms of hydrogen, and this thing is basically telling me that there's two atoms of hydrogen joined together. Now this number in subscript, this small number basically tells that they're joined together chemically. And now this thing is hydrogen gas. That was hydrogen atom. Hydrogen atoms are very different from hydrogen molecules. Hydrogen atoms are highly reactive, but hydrogen molecules are pretty stable. And we know why that is. That is because their last shell is complete. All right, where's the covalent bond? So the thing is that this thing is a shared pair of electrons. So this is a shared pair of electrons. And when they shared it, they form a covalent bond. We call this the bond pair. But where's the bond? I don't see it. Basically, the bond, as I told you, remember, any bond is between a positive thing and a negative thing. And it's a strong force. So if you're able to identify the positive thing and the negative thing, you know what the bond you have. So over here, the positive thing is this hydrogen nucleus. In fact, there are two nuclei. So each of them is pulling on this bond pair. So this hydrogen nucleus is pulling on these two, and this hydrogen nucleus is pulling on these two. And this is covalent bond. So what is bond? A covalent bond is the strong force of attraction. So it's the force of attraction between, you need to know what the positive thing is, what the negative thing is, between shared pair of electrons, the sharing part is important, and nuclei or two nuclei. Now here's the interesting part. I said shared pair. Some people say mutual sharing. That doesn't have to be. Both of them don't have to give an electron. Sometimes electrons come from, the whole pair comes from just one atom. And we will consider a case of carbon monoxide for that. So that's the case. You have two atoms coming together, sharing pair of electrons, and the force that they have between the two nuclei and that shared pair, that is basically covalent bond. How is it made? It is made by sharing of electron pairs. Electrons are always shared in pairs. That's something you should remember. All right, so we have shared pair of electrons from the last shell, and there are two nuclei that are pulling on them, and that is how you get the covalent bond. All right, so it usually happens in just non-metals. What if we don't have two atoms that are the same? For example, in this case, you have hydrogen bonding with hydrogen. What if I do not have that? What if I had a hydrogen atom and a chlorine atom? So I would have a hydrogen atom with one electron in the last shell, and chlorine atom which has 6 electrons in the last shell. Now here's the thing. What I'm going to do is I'm going to draw chlorine using a different symbol. Instead of drawing circle for this, I'm going to use cross for chlorine. Now that's perfectly fine if you draw cross for hydrogen and circle for chlorine, because the whole point is to show that they're from different elements. These electrons are identical. There's technically no difference in them. It's just that one is for one element and the other is for the other. And when they come together and we say this, we read it hydrogen atom and chlorine atom make, and this is what they're going to make. What they're going to do is they're going to share one electron. Hydrogen needs one, chlorine needs one. So they'll just share one electron each, giving us this thing. There is hydrogen here, chlorine here. Always start by putting in the electrons that they share. So this shares one, this shares one. And chlorine had 7 to begin with, so 7 on the outside. And that is how you know that you have formed HCl. Now it doesn't have to be this way. You can draw, as I said, you can have different symbols for it. But as long as you're sharing this equal number of electrons in here, and there's no difference as far as the number of electrons is concerned, you're drawing all the electrons required. It's perfectly fine. Now, there are two kinds of pairs here. This pair, which we'll call bond pair, and this pair, which we'll call lone pair. Now, lone pair is from the last shell, but it doesn't take part in chemical bonding. It's just there, all right? And as far as we are concerned, it doesn't take part in chemical bonding, but it has a very important role to play in organic chemistry and in later stages of chemistry that you'll study. So just identify lone pair, bond pair. Now, all of this is fine, and this is dot and cross diagram, but it doesn't always have to be shown like that, especially when you have bigger molecules. Dot and cross diagrams can be cumbersome to make. So what we rely on is Lewis structure. Lewis structure, again, it's named after Gilbert Louis, who was pretty much one of the greatest chemists of 20th century. And Louis gave us a simple way of drawing these. So instead of drawing these circles and these large diagrams, I can simply say there's hydrogen, there's chlorine, and they're sharing one pair. So this line basically shows one bond pair. That's what they're showing. So if we were to do the same thing over here, basically this is the same thing. So HCl with one line in the middle showing one pair. I could show the same thing for this hydrogen. So there's one hydrogen atom and the other hydrogen atom sharing one pair of electrons. I'll show like that. Now, what if they wanted to share more? That's perfectly fine. You can share more. So for example, oxygen is short 2 electrons. It has 6 in the last shell. It needs 2 more. So when 2 oxygen atoms come together, they overlap, and each of them, because they need 2, each of them gives 2 electrons. And here is what you get. Both of them are going to come together and they're going to form this oxygen molecule. All right, so this is the oxygen molecule, as you can see. So what's happening here is that each oxygen atom is sharing 2 electrons, and those are the 2 bond pairs that they have now. Now, because there are 2 bond pairs, we show oxygen and the other oxygen with 2 lines in the middle. And these 2 lines are basically telling me that there is 2 bond pairs, 4 electrons shared. Of course, there are lone pairs, and there are 4 lone pairs in this case, and that's perfectly fine. What if you wanted to draw it for nitrogen? Again, we'll do it for nitrogen, but before we do that, hold on. How do we write the formula of oxygen? So oxygen is O, and there's 2 of the same thing, so O2. If we were to do it for hydrogen and chlorine, because we have 1 hydrogen and we have 1 chlorine joined together, we'll just say HCl. All right. Now, I would give you a few more examples of this, and let's just study them. So these are some diagrams of these compounds, different ones or different elements. And let me show you how that works. So over here, we have many important molecules, simple molecules. So what's happening? Let's study them. Hydrogen has 2 hydrogen atoms. We write them as H2, and each of them is sharing 1 electron, and that is why we have this 1 bond pair. And the dot and cross diagram shows this. In HCl, we have lone pairs, but we also have bond pairs, and that is why H and Cl have 1 line in the middle. The formula is still HCl because there's 1 H, 1 Cl. Now for chlorine, you have Cl2. Why? Because you have 2 chlorine joined together. And there is 1 bond pair in the middle because they're sharing 1 pair of electrons. Why is they sharing 1 pair of electrons? Because every chlorine needs 1 more. They're in group 7. Let's look at water. Water is interesting because water has 2 atoms of hydrogen and 1 atom of oxygen. 2 different elements coming together in different numbers. So what's happening here? Let's try to draw this structure and let's see how this works. Now, every time you have different elements coming together, just write down the formula. So you have H2O. What's happening here? I have hydrogen. And how many does hydrogen need? Hydrogen needs 1 more. How many does oxygen need? Oxygen is group 6. To make 8, it needs 2 more. All right, so here's the thing. Here's the radical idea. The one that needs more, put it in the middle. So oxygen needs more, I'll put it in the middle. Okay, no electron show, so on and so forth. Now draw the others out around it. So hydrogen here, the size doesn't matter. You can make a bigger one or a smaller one is fine. Okay. Now start putting the bond pairs. So the left hydrogen needs to share 1, it shares 1. Right hydrogen needs to share 1, it shares 1. Okay, now let's start with the lone pairs, the ones that are not involved in bonding. Oxygen is in group 6 It had 6. It has shared 1 with this hydrogen, 1 with the other hydrogen. It's left with 4 electrons. So we'll draw 4 on the outside. Now remember one thing, many students, what they do is that they put these bond pairs and then they forget about the lone pairs individually and they just draw 6 electrons. That's wrong, because the last shell has all the electrons, whether they're lone pairs or whether they're bond pairs. So you have to make sure that 6 is the total number of electrons of oxygen. And that is the case over here. So that is how you draw them. It's the same case with ammonia. For example, if you look over here, ammonia has nitrogen, hydrogen, and the other hydrogen. So again, how did they draw it? Nitrogen needs 3, hydrogen needs 1. So naturally, nitrogen goes in the center. And then we take hydrogen all around it. We start by putting the bond pairs. So bond pairs here for each hydrogen and then the lone pair. So this is, if you were to look for an algorithm, a method of making these diagrams, then here's what you should do. Identify which one needs the most. So atom with greatest requirement goes in the center. Okay. With others around it. All right. Then draw the bond pairs and then draw the lone pairs. And there you go. That's all you need to do. And if you're able to do that, you're able to draw any atoms you need. So I'm going to give you a few examples to practice. So these are some that are required in your syllabus. So for example, you should know how to draw carbon dioxide. You should also know how to draw CH4. But this method will work regardless. Of course, we have seen ammonia, we have seen this one. I would also implore that you try ones that have more than one atom together. So for example, try this one, C2H4 or C2H6. And if you're up to a challenge, try HCN. All right, so I'm going to give you 5 minutes to practice this and then we'll resume our class. Thank you so much, Travel Music. I really appreciate that. Thank you. All right, so let's start with carbon dioxide. Again, carbon is the one that needs the most electrons. It has 4, so it needs 4 more. So we're going to put carbon in the center. The other 2 oxygen are going to go outside. So that's what we'll do. So, and here's the structure. There you go, carbon dioxide. Now you can see over here that carbon is in the center, oxygens are on the side, and each carbon needs 4, but each oxygen needs 2. So that is why we start by taking 4 of this, 2 of this, and we start by putting carbon in the center, oxygen on the side, and every oxygen needs to share 2 electrons. So 2 of oxygen here, and 2 of oxygen being shared with 2 of carbon here. Same case over here, so you have 2 bond pairs. Now, let's talk about lone pairs. Oxygen had 6 electrons, so 2 shared, 4 remaining, they go on the outside. The other oxygen has the same thing. Carbon had 4 electrons, it has already shared 4, so no more lone pairs. And the structure, the Louis diagram would go like this, that you have carbon in the center, 2 oxygen on the side, and 2 lines to show 2 pairs with each of them. And CO2 to show that you have 1 carbon, 2 oxygen in the whole molecule. Similarly, if we had CH4, so CH4 would look like this one. There you go. Again, carbon needs 4 electrons, so carbon in the center, hydrogen on the side because it needs just 1 more. And then hydrogen has 1 electron to share, so hydrogen's electron goes there. And the other one is also for every one of them. And then you have carbon, which has no lone pairs left out because it shared all 4. So there you go, that's methane. Similarly, let's try ethene. Again, you don't need to know the name at this stage. We will talk about it when we get to organic bonding. All right, so this is ethene, C2H6. I gave you this formula, but this is another way of writing it. And this is called structure formula. We'll talk about it again in organic chemistry. So again, what's happening here? You have 2 carbons, both of them needing 4. So both of them go in the center. And then hydrogen goes on the outside. And this is how you're able to get carbon sharing 1 with each hydrogen and then 2 with each carbon with each other. And that is how you get this structure. Now I gave you a challenging one. here's how we should do it. Now C2H6 is also pretty easy. What's happening here is that you have two carbons, so both of those carbons go in the center and hydrogen on the side. Because there's 6 hydrogen, every carbon gets 3, equal distribution. So there you go. Now what's happening here is that hydrogen needs to share 1 more electron, so it shares 1. Every one of them does it. Carbon needs to share 4, so 3 here. So 1 remaining, that is what they do with inside. Now they don't have any lone pair, so there's no lone pair here. This is ethane, which we wrote as C2H6. Now the last one that we had was 8CN. This is interesting because this is the first one in which we have 3 atoms coming together. So let's try it. And if you're somebody who's trying it just now, I would suggest pause the video and then try it and then resume it. All right, so here we go. Let's write down the number of electrons that they need to share. So hydrogen needs 1 more, carbon needs 4 more, nitrogen needs 3 more. How am I knowing this? The total should be 8, right? Hydrogen has just 1, so it shares 1. Carbon is in group 4, 4 plus 4 is 8. Nitrogen is in group 5, 5 plus 3 is 8. So that's why it needs 3. If it was oxygen, oxygen is in group 6, so 6 plus 2 is 8. All right, carbon needs the most, it goes in the center. Okay, and then the others around it. So 1 hydrogen here. Again, the size of the atom doesn't matter as long as you're getting the enough space to draw all the electrons. Hydrogen, nitrogen. Hydrogen needs to share 1, so it shares 1. Nitrogen needs to share 3, so it shares 3. Don't worry about which one has cross and which one has circle, it's perfectly fine. And do we have any lone pairs? Hydrogen had 1, it has shared it. Carbon had 4, it has shared them all. Nitrogen had 5, it has shared just 3. So it has 2 remaining. So I'm going to put 2 on the outside. You could have used a cross, that's perfectly fine, no problem there. All right, so there you go. We have drawn 8CN. The Louis diagram would be HCN, and hydrogen and carbon are sharing 1 pair, so that is 1 line. Nitrogen is sharing 3 pairs, so 3 lines, and there you go, that's 8CN. So those are all the regular bonding things that we have seen. Now I'm going to introduce to you a very unique case, and it is one that is very rarely tested in O levels or IGCSE. As far as I remember, I think it was tested just once. But again, because I don't want to leave anything out, I will make sure that you all also know this. All right, so this one is carbon monoxide. CO. Now this is an unstable compound, and another thing you should know about it is that it is poisonous. It causes blood cancer. If it goes into your body, it just hijacks the red blood cell that we have and binds with the hemoglobin in there, and then it's very difficult to take it out. This one is called silent killer because of this, and the Murray tragedy that we have recently, it was because of carbon monoxide poisoning. So I would suggest that you study about it and make sure that you're safe if you are in an environment like this. Also, it's very important that you use carbon monoxide detectors in your closed spaces at your home and all that. All right, so what does it do? Carbon monoxide is unique in the case, in our syllabus at least, that it has different number of electrons being shared. So for example, in HCN, hydrogen shared 1, carbon shared 1, carbon with nitrogen, each of them shared 3. But that's not happening here. Carbon needs 4, oxygen needs 2. So there we go. We put carbon here, oxygen here. All right, carbon, oxygen. Carbon needs 4. So let oxygen share 4. 1, 2, 3, 4. Oxygen needs 2. So let carbon share 2. The bonding is complete. Let's draw the lone pairs. Carbon has 2 electrons remaining, 4 that it had. It has already shared 2, so 2 on the outside. Oxygen had 6 total electrons, and it's able to share 4 of them, 2 on the outside. And this one is unstable, and this is carbon sharing 3 electron pairs with oxygen. And that's a Louis diagram. But here's the interesting part. Do you notice that both the electrons are coming from just one atom, that is the atom of oxygen, While this is a bond pair, this is a unique kind of bond pair. We call them dative bond, or it's also called coordinate bond. Now again, examiner will not directly ask you to question about this. But what you should know is that if a situation like this comes, you don't need to worry about it. This is something that you should be familiar with at least, so you don't have any surprises in the exam. So what did we do? We just look at the requirement of these atoms, and because we know the compound exists, it must be the case that they are doing some kind of bonding, which may not be exactly what we've seen before, but it is still something that is there. All right, now that is the structure that they ask us to draw. Sometimes they ask us to count molecule and the electrons in the molecule. So I'm going to take an example here, and that is sulfuric acid. Let me Google sulfuric acid molecule. Can't really find a good diagram, but all right, I guess this might do. All right, so we have a sulfuric acid molecule here. This one, they will not ask you to draw, obviously, because this is not required at this stage. But what's happening here is, by the way, I should attribute that I got this diagram from study.com. So thank you so much, study.com, for drawing this. All right, so we have hydrogen sharing these things with sulfur, oxygen. It's a big molecule, all right? It's one of the most used chemicals in the world. In fact, probably the most used chemical in the world after water. All right, so what's happening here? How many lone pairs do we have? So let's suppose there's a question that how many lone pairs do you have? So for that, what you should do is that you should put the electrons on every atom that we have. So oxygen had 6 electrons. It has shared 2, so the remaining 4 go outside. And that's for every oxygen, right? This oxygen, this oxygen. Now this oxygen had 6 electrons to share, so 2 pairs shared. That means 2 electrons are shared already, so 2 on the outside. All right. And then sulfur in the middle had 6 electrons, but for some reason it has shared more than that, right? You can clearly see that sulfur over here has what? 1, 2, 3, 4, 5, 6 pairs of electrons. And that is nothing that you need to worry about, okay? Because it's fine. It is okay for some atoms to have more than 8 electrons in the last shell. And again, that is something that you don't need to worry about. Just know that that exists. Be familiar with it. There shouldn't be any surprises coming to your way when you're in the exam. Of course, they will not ask you to draw it or explain why this is working out. Why does this exist? We will study that. Every question has an answer, but it depends on the academic level. At this stage, we just need to know that this molecule does exist like that, and sulfur has more than 8 electrons. There are others with more than 8 electrons in the last shell. All right, so that's the case over here. Let's count how many electrons are involved in bonding. So how many bond pairs do we have? So 1, 2, 3, 4, 5, 6, 7, 8. 8 bond pairs. So that is 8. So 16 electrons in bonding. All right, so there's 16 electrons in bonding. How many lone pairs? 2 on each oxygen. So that is 8 lone pairs. So that is again 16 electrons not involved in bonding, but from the last shell. Now, examiner might ask that how many electrons are not involved in bonding. And for that, you should count these, sure, but I'll give you a shortcut to do it. Just take the electrons from the proton number of each atom. So hydrogen is 1, oxygen is 8, sulfur is 16. So the total comes out to be 1 plus 8 plus 8 times 4, in fact. Let's just do it that way. See, it's faster. So 1 times 2 because 2 hydrogen, 8 times 4 because 4 oxygen plus 16. That gives me 2 plus 32 plus 16. That is, I think, 50. So I have 50 electrons. Out of those, 16 are involved in bonding because I have 8 pairs. So 16 subtracted, I'm left with 34 electrons not involved in bonding. Now, if you notice, it's not clear where those 32, 34 are, but sulfur has electron in the third shell being shared. What about the first shell? What about the second shell? Oxygen is sharing from the second shell. So what about the first shell? So that is why it's very important for you to know how to count these electrons, because examiner can ask you in an MCQ or otherwise how many electrons are involved in bonding, how many electrons are not involved in bonding. For bonding, it's perfectly fine. Take the bond pairs, multiply by 2 and you have your number of electrons. But for others, just take the total proton number of every atom, add them all together, and you have the total electrons. Subtract the bonding electrons and you have your required remaining ones. Alright, so all of that is good for simple molecular substances, but how do these things technically behave? Now, the behavior of these substances is important to understand. These have two main characteristics. Number one, they don't have any, so here's the thing, unless the question specifies it, all covalently bonded things that you see will be simple molecular. All right, so unless the question specifies, so graphite, diamond, and silicon dioxide, taking those out, the remaining ones, unless the examiner says that, all right, this has giant bonding, or this has a structure similar to diamond, or this has a structure similar to graphite, everything that you'll see in covalent bond will be simple molecular. They don't have any giant lattice. There's no lattice there. There's no structure that is fixed over there. So what happens? These things, so for example, we talked about hydrogen, right? So hydrogen molecule, so this is one hydrogen molecule, and this is another one. But do they have anything to do with each other? Turns out they don't. All they want to do is they have weak intermolecular force of attraction between them. I'm going to call that weak IMFA. Intermolecular force of attraction. This is one molecule. This is one molecule. And this molecule, each of them is very stable on its own. But with each other, they don't really have much to do. So they have very strong covalent bond here. So this is a strong bond, okay? This is covalent bond. This is inside the molecule. And this is outside the molecule. And between one molecule and another, you have intermolecular force of attraction. We also call them van der Waals forces or London dispersion forces in some cases. But these are weak. You have to remember this. So because the forces between these molecules are weak, they don't really require a lot of energy to break. So what does that mean? That means you can heat it and you supply enough energy at low temperature. So these are broken pretty easily, which is why simple molecules have low melting point. And that is first property of these things. Simple molecular substances, they have low melting points, low densities, all right? And all of that because they have weak intermolecular force of attraction, which can easily be broken down, all right? So that is why they tend to be gases, liquids, or sometimes solids with low melting point at room temperature. All right, now again, melting, boiling, density, all of that is a physical property. So in physical property, the bond does not break. In this case, the intermolecular force is the one that is going to break. Okay, now there's only one conductor for covalent substances in our syllabus. That is graphite. And I'm talking about a pure substance like that. Now there are other things that are impure and covalent that conduct electricity. So I'll quickly talk about that. When it comes to conduction, they don't have any free electrons. So they're bad conductors. As pure substances, they're bad conductors. All right, so they don't have free electrons. So no free electrons is the reason that they don't conduct. And low melting point because they have weak intermolecular force of attraction. And that's it. That is the property that we need to remember. For example, in group 7, the melting point of fluorine, the smallest atom, which has very strong bond, is minus 220 degrees Celsius. And chlorine is minus 101, and bromine is minus 7, and iodine is 114. Now 114 might seem a lot, but the molecule itself is really, really big. So there is some trend in physical properties, and the forces do change a little bit from one substance to another. For example, iodine has stronger intermolecular force, but chlorine has weaker intermolecular force. Again, why is that? We don't need to get into that. But just know that intermolecular force of attraction is generally weaker compared to ionic bond, metallic bond that we have seen before, which is why their physical properties are going to be just like this one. Now, there is a class of covalent substances that does conduct if they're impure, and that we call acids. So acids, water, both of these things conduct when impure. And the reason why they do that is because they ionize. So they have free ions, and because of them, they're able to conduct. In pure form, they will not be able to. But all acids and water, if they're impure, if they're mixed, in fact, mixed with each other or mixed with something else, they can form ions, and these ions can conduct electricity because they'll be free. So for example, in the case of water, these ions are H positive and OH negative. So water, as you know, is H2O. When it is impure, it can break down and it can form H positive and OH negative. This does happen in pure water as well, but to a very small extent, so we don't really count it. And then in acids, they all give H positive ion, and that ion is able to move around and conduct electricity. And there are other ions as well. So just remember that acids and water, when they're impure, can conduct because of free ions, but in pure substances, covalent substances, molecular substances, will be bad conductors because they don't have any free electrons. All right, so that is the simple molecular substance. Now, what about this very first case when we were talking about it, this carbon? Carbon has 4, carbon needs 4. It's a very interesting case over here, because what carbon does is that because of this strange case where it needs exactly the same number of electrons as it already has, what carbon does is that it shows us a new kind of substance which we call allotrope. What's an allotrope? Allotrope is 3 things. Allotrope has same element, so it must be an element, not a compound. Same state, so it must be solid if all allotropes are solid. It must be gas if all allotropes are gas, but different structure. And this is a very interesting case. Diamond, for example, is very versatile in this case. Diamond has so many allotropes. So 3 of them you are supposed to know at this stage, but there are others that go way beyond it. For example, diamond is 1, graphite is 1, and the third one is fullerene, which is named after, I think his name was Fuller. He was an engineer, and he was the first one to draw a structure based on this structure of the fullerene. He drew a geodesic globe or something. Anyways, so these are the 3 things for this. Now, what's the structure like? For diamond, the structure, as you are well aware, is something like this one. Okay. And for graphite, the structure, again, you might have seen this before, is this one. Okay, let me shorten this so they can be easily compared. And lastly, we have fullerenes, and fullerenes might be new for you, but that's again nothing to be surprised of. Fullerenes are like this one. Now they're all carbon. That's an interesting thing. They're all carbon, and they're pure carbon, 100% pure carbon, but their structures are radically different. Their properties are radically different. What's happening here? We call these giant structures. The structure of diamond, the structure of graphite, we call them giant structures because they have these lattices that grow and they continue for really, really large number of atoms, billions and trillions of them. So what's happening here? Giant covalent substances are basically massive compounds or substances with very strong covalent bonds. So this one, the solid lines are very strong covalent bonds. Okay. So this one is also very, very strong. In fact, these make some of the things with the highest melting points in nature. All right, so what's going to happen? Because of this very strong bond, they have high melting point. In fact, very high. Some of them have even higher melting points than many metals. So very high melting point. Why? Because they have very strong carbon to carbon attraction. Carbon to carbon bond is very strong, which is very difficult to break. So if you want to melt it, you have to break all these forces. You have to break the whole structure, and that structure can be difficult to break. So no wonder they have very high melting point. And then diamond, for example, is very hard. Why does something become hard when there is no flexibility in it? And because diamond, every atom is joined to 4 others, it's very difficult for it to maneuver, to move around, which is why diamond can be really hard. In fact, diamond is used in many drill bits. So what's a drill bit? For example, let me show you a drill over here. So what's happening here is that this guy is trying to cut through a rock, okay? And he has a saw, and that saw has diamond on its edges. So yeah, so there's the case. So he's trying to cut through a rock, and you can imagine how hard rocks can be. So this saw has small diamonds on the tips of it. Of course, diamond we get mainly from Africa, and I think the biggest producers are Russia and Botswana. And yeah, so it's a really clean process when you get diamond from kimberlite, which is the ore for diamond. Ores are basically rocks from which we get these metals or other precious things. So diamonds, although they're mined throughout Africa, we get kimberlite, and that kimberlite is then crushed, washed, we filter things, and the whole purification techniques part that we saw, we use all of that. And once we get that, we in fact use X-rays to find diamonds. And then there are obviously 4 C's on which every diamond is checked, like its carat mass, its clarity, how clear it is, and how much does it reflect light, and what's the cut like. So color, of course. So these 4 C's basically tell us what the structure of diamond is and how valuable it is. But diamond, it doesn't really have to be like valuable for jewelry. It's also very valuable in industry. For example, this is the case where we use it in a drill bit. Okay, so it is tip of this drill, that is where we have diamond. All right, so that's diamond. So for example, while we get it raw in jewelry, you might get something like a very beautiful cut. For example, this one. And this is a bad diagram, but yeah, these can be very shiny and very beautiful. All right, what about graphite? Imagine I just showed you some diamond. What if I told you that this thing on the left is actually the same substance as this? You wouldn't believe it, right? Because it doesn't seem right. It doesn't seem that one is very shiny, clear, it has many colors, and the other is a dull black thing. In fact, that's very dark, the other thing. And that's graphite, but it's only the structure of that thing that makes it so different. Graphite has these layers of carbon atoms, and every carbon atom, while diamond has 4 bonded to it, every carbon atom in graphite has 3 other carbons bonded to it, which basically means that this carbon is going to share 3 bonds with each other. When you pick any one, they're going to share 3 electrons with each other, and the 4th electron is free. So there is 1 free electron for every atom. So they are good conductors. Diamond can't conduct. Diamond has 4 electrons, and every carbon in diamond has 4 electrons, which are all shared. But graphite has 1 free electron, so it is able to conduct because 1 free electron per atom. All right, so graphite is a very exceptional thing, which is why we use graphite in cells, in electrolysis, in batteries. We use graphite all the time. Yeah, so that's what graphite does, but it still has very high melting point, because even though the 4th one, this one is weak, and we can call it van der Waals force, this one is weak van der Waals force, but the other 3 are not. Other 3 are still covalent bonds, and they're very strong. So that is why with graphite, you need to supply a lot of energy. Not as much as you need for diamond, because diamond has more bonds, but these bonds are also needed to be broken down if you want to melt it, which is why graphite also has very high melting point. There's these layers of hexagons, and these layers can slide. So that makes graphite very soft, because layers can slide. Okay, so these layers have weak forces between each other, so they can slide. And the 4th unbonded electron, as I've already told you, it's free, so it can move along this layer, and they conduct electricity. Now the third one, which is fullerene, is basically a large ball of atoms. So each atom is very strongly bonded to three others, just like in the case of graphite. So the 1, 2, 3, for example, this one, 1, 2, 3. This is called a fullerene. This is a molecule. For example, this one is C60. 60 atoms of carbon all joined together to make this football kind of thing. So this structure is similar to graphite, but it's not as strong. And its fourth electron is also free. And we say that it is delocalized, just like the one in graphite. So it's also a good conductor. Same reason, all right? But this is it has low melting point because it has weak intermolecular forces, because this is a molecular thing. So it behaves exactly like other molecules that we have seen. So if you understand carbon, you basically understand the structure of all covalent substances, to be honest, because this is how these things behave. And diamond has such versatility, such variety to offer, that you can understand molecular things there, giant covalent things there, giant covalent things conducting electricity. Now let me share something. There are diamonds that conduct electricity, and that is because they are impure. They have impurities in them which make one electron free for some carbon atoms in there, not all of them, some of them, and they start to conduct. So again, examiner might bring that for you, and you might get confused that, wait a minute, diamond did not conduct electricity. But if you remember this, that simply means that you are somebody who did not really understood the concept. You preferred the easy way to just memorize things. But just remember, what is the core reason diamond doesn't conduct? It's not like diamond doesn't want to conduct or anything. It's not like that. Diamond just cannot, because all electrons are engaged in covalent bond. But if you were to free some of them, why wouldn't they conduct electricity? They can move, they can carry charge, so they will. So these properties are not as rigid. If you change the reasoning, if you understand the reasoning, anything can do anything as long as you give it that reason. All right. So graphite has free electrons. If you bind it to something that doesn't allow those electrons to move around, graphite can't conduct electricity. So these things are very fluid. You just have to understand the underlying principles, the governing principles, that graphite conducts because it has free electrons. Fullerene conducts because it has free electrons. Diamond doesn't because it doesn't have free electrons. So it is all about free electrons. It's not about diamond or graphite or fullerene. Similarly, something being hard or soft depends on its structure or how strong the forces are. Are they keeping it the way it is? And if they are, then the thing is going to be hard. If they're not, the thing is going to be soft. For example, graphite has free layers, right? They don't have any strong forces. So we use graphite as a lubricant. All right, so that's pretty useful, graphite. So yeah, so that's the thing. So yeah, so we are done with covalent bonding, and I hope you understand this. If you have any questions, do let me know. All right, and yeah, I'll see you in the next class tomorrow. Thank you so much for attending. Take care. Allah Hafiz.